Let's talk a little bit about recurrent neural networks. Recurrent neural networks are a special kind of neural networks. So before then, we will say something about neural networks in general. We now cover in very general and informal terms some basic ideas about neural networks to help the understanding of the rest of the discussion. So, to give a simple description, we can say that a neural network is a composition of elements that we call artificial neurons. And an artificial neuron is described in the picture on the left. If we start looking at it, we see that from the left side we have some input elements that are described with these little circles. So we have numeric inputs that are given from the outside to our neuron. And the first thing that happens to these inputs is that each of them is multiplied by a quantity, which is put here on this line. And after being multiplied, each of them for its own weight, these are the names of these parameters. After being multiplied for each one for its own weight, they reach a sum operation that takes all these terms and makes an addition. The addition, after being incremented by another value, which is another parameter which is called bias, so the letter B. This term is the input of a function called activation function, and the output of the activation function is the output of the neuron. We can see the same concept in this formula, where we have our input for each one for its own weight. We have the total, and we have the bias, and these all together is input to the function f, and this is the output of our neuron. The function f most of the times is a nonlinear function. So what is a nonlinear function? A nonlinear function is a function that is able to have some tricky, interesting, and useful behavior, and we see some examples of them on the right. So for example, at the top we have the sigmoid, which is a function that has broadly three areas. For the one part, the value returned by this function is always 0. On this part, the value returned by the function is always 1. In this intermediate section, we see that the function progressively grows from 0 to 1. So this function is kind of able to give us like an off neuron, or maybe a on neuron, or maybe a neuron in an intermediate state that is giving us an intermediate value. If we look at the bottom, sorry, we have another nonlinear function which is called the rectified linear unit, or ReLU, and this has two areas in which it has two different behaviors. If the x is less than 0, then we have that the value of the function, so the output of the neuron, is always 0. So the neuron is off. If the value is greater than 0, then we see that the output value is the same as the input. So for positive values, the neuron is kind of doing nothing, just passing the input straight to the output. And if we go back to the expression that describe our neuron behavior, one thing to notice is that all the inputs are fed to this sum operation, and the sum is commutative. So among the inputs, there is no notion really of position or positionality or closeness or proximity. So all the inputs are equal, and input 2 and 3, for example, are no closer than input 2 and 176, if there is one. We give a closer look to another nonlinear function called Tinyh, which we will see adopted in the rest of the presentation. And Tinyh has three areas that we can see. And if we have inputs that are far enough from 0 on the negative side, Tinyh is giving an output value which is close relative of -1. If we have values of x that are far enough from 0 on the positive side, we have Tinyh that will give us values that are around +1. In between, we have that the value of the output is growing with the x, and it's somehow not too far from the input value. We can see some examples here on the left. So for negative values, we get values which are very close to -1. On the bottom, we see positive values, and we see that we get values which are close to +1. In the middle, we see that, for example, for 0 we get 0, for -0.5 we get something in that range, for -1 we get -0.7, and we get symmetrical values on the other side. So in this area, we get values that are sort of relatives of the input value, and we have this intermediate area where the function is progressively growing, and we have two extreme areas where the function is just giving us an off or on neuron as outside as output value. Having introduced a basic artificial neuron that we can see here reproduced on the upper right, we can try to ask ourselves what are the elements that that we found in this technology, and what are the elements that make it so powerful and able to produce amazing results. So what we know and what we have seen so far, and that we have elements able to process numerical data. So we have this input numerical data that we feed to the neuron, and we have seen that there is this input data gets multiplied by some parameters, and then everything is added up. Then we have said that we have these interesting functions that we can choose from, which most of the time are nonlinear function. So here we start to find something that is able to probably gives the single neuron and then the network some interesting and smart behavior. But there are still two elements that we haven't talked about, and then we are going to cover next, which make this technology very powerful. The first element is the architecture of the network. So we have seen the model of a single neuron. We have to take into account that networks are organized in very large and deep architectures, and they can be composed of many neurons, such as tens of thousands or hundreds of thousands, or even you can hear the word millions of neurons. And another key aspect of a neural network that we will talk about are these parameters that we saw, which multiply the input, because these parameters is what is learned during the training of the neural network. So these parameters are what makes the network able to learn how to solve the problem that we are going to tackle with the specific model that we are working on. The most typical and common way to arrange neurons in a neural network is to have several layers, as we see in the example on the upper right. So here we have a network with 3 layers. On the first layer we have some input values, and then we have 2 proper network layers. The first are values that are computed from the input layer, and then from the hidden layer we can calculate the output layer values. And for each of these nodes you see happening what we saw before for the single neuron that we considered. We see that these input values coming from the previous layer get multiplied by a parameter, which is considered to be here on the arrow, and then they are added up together. We will see all these kind of networks, and we have to take into account that they are usually represented with a much more compact representation that we have to understand. So if we look at the picture on the left, we see a small example with the numbers. So if we look at this neuron and we consider all the inputs that we have 3, and each one is multiplied by the weight that we see here on the arrow, and then the total is calculated, and the total is 0.9. And an easier way to represent all these is using matrix multiplication. So what we see here is something on the right which is totally equivalent. So what we can say is that we have layer 1, which are the values that we see here. And this layer 1 gets multiplied by a matrix of weights. And the matrix of weights is just all the values that we have here on the arrows, and they are organized in the proper way. So, for example, for each row, we are the weights that are incoming into a particular output neuron. So we can see that if we take all these elements in this row and multiply the first by the first, and then the second by the second, and the third by the third, and we add everything up, we get 0.9. We do the same for the second row, we get 4.9. We do the same for the third row, we get 0.5. We can see all the expressions here on the lower right, and we see that the input layer that we had, layer 1, is made of the red values. So these red values are always multiplied by the first row, then by the second row, and then by the third row. And we get the first value of the output vector, the second value of the output vector, the third value of the output vector. So the bottom line is that we must get used to seeing this kind of expression. A matrix of weights multiplied by a network layer gives us the next layer. And sometimes we see switching of these two terms because you can switch rows with columns in this table that we call matrix, but doesn't matter, it's not really relevant. We just have to remember that when we see two layers of a network, we multiply the first layer by a matrix of weights, and we get the next layer. As simple as that. We have discussed a fair bit about neural networks, but we haven't tackled probably the most relevant capability, which is the ability to learn how to solve a specific problem. The approach that is used with neural networks is called supervised training. And supervised training is based on a set of representative input patterns. In other terms, we must have a case history, history of occurrences of the problem that we want the network to be able to solve. And for these cases, we must have the input values. So we must know which were the values of the input for each particular occurrence. And also we must know what was the actual true, correct value of y of the output for that particular case. So from this history, the network will be able to learn using a process that we see here drawn in the lower left. And everything starts with the network having random values for the weights, for the parameters, because learning and training for the networks means finding the proper value for the parameters, because we have said that the parameters are the only part which is not fixed, and it's able to modify the behavior of the network in the proper way. So initially the value of the parameters is random, and what we do is that we provide the network some input, and we let the network calculate the output. The first time that we do this, of course, the output value, we expect it to be wrong, to be very wrong, with probably a random value. So what we do is that we have the desired value for this input that we have provided to the network. Because remember that for the case history that we use, we must have the true results, and these are called labels. So if we compare the output with the label, we are able to derive the difference, to understand how wrong we were, and from this difference, the training algorithms that we use are able to adjust a little bit the weights, to modify the values of the parameters, to make them a little bit more useful in getting closer to the right value of the label. And this is of course a part where mathematics is relevant, and here we deal with functions of several parameters, and we deal with partial derivatives, and there is an approach that starting from the error on the output is able to derive all the updates that is recommended, is useful to make in the previous layers of the network that can be many. So having done this adjustment of the weights, following these algorithms and the family of algorithms that is used is called gradient descent, we again fire our network on another case and we calculate the output, we compare to the correct result and we get the error. And from the error we can do another very little adjustment to our weights. And this cycle is gone through many times because we can have thousands, hundreds of thousands, millions of cases, and we can go through our case history hundreds of thousands or hundreds of thousands of times. So the key here is that we make very small adjustments and we go through the cycle many times, and hopefully at the end we see and we judge with some criteria that we start getting errors that are smaller and smaller and smaller, and the network is learning and is making small errors, so the answers start to be what we can say in a word correct or almost correct or correct enough, we would say, and we can stop the training and we can put the model in production, we can use the model and we can use the neural network for the prediction phase, where we apply the neural network to new cases for which we don't know the true label, the true answer, the correct answer, but will be the neural network to provide the correct answer to us. We want to now focus a little bit on the process flow, on the way of thinking that dealing with such kind of models allow, which is a little bit different from probably how every day we approach typical problems. So the idea is that we must have a problem which must be possible to express in terms of numerical input and finding the good values for some numerical output. And of course, input and output can also be an encoded picture, an encoded text, can be video, audio. And at step 3, we see that the key element is, as we said, we need to have a good case history, to train the network. If we have these, we then design a suitable neural network model for the kind of feed-forward or dense networks that we have seen. It could mean choosing the number of layers, the number of neurons for each layer, the activation function to be used, and so on. And then we are good to go, and we can train the network on the cases that we have, and then we are done. If the testing of the network show us that the errors are small enough and the predictions are good enough, we can use the network to solve future new occurrences of the problem. And the main thing to notice here is that we didn't actually really dig into the problem and a way to solve it. And if we want to distinguish cats from dogs, we are not really analyzing the differences in terms of pets anatomy, or if we want to guess which credit card application will give not many problems in the future. We are not discussing how personal finances are handled, or we are just using the data that we have, and from the data we are building ourselves a solution that we can use. And we will find this approach in the rest of this discussion, and in the models that we will see. So I think it's useful to notice this different approach, this very different approach that neural networks models and in general machine learning allows you to do. We have seen and understood what neural networks are, and we see here the kind of neural networks we have discussed in the upper part of this slide. We have our example of a neural network that we can use to predict, to decide on credit card applications based on the age, the salary, education, and so on of each customer that apply for a credit card. To use this network, that we don't care how it is made, it's just a black box for us. To use this network, we provide the input, and the network gives us the output, which is yes or no, 0 or 1. So if we look at the picture on the right of a feed-forward network, we can say that we have an input which is made of probably some numbers, and we have the network, and the network is giving us one number of some numbers and as output. So we see here the input and the output that is represented as vectors, where vector is a string of numbers that like the ones we saw before. The main thing is that if we want to apply this network to many customer, we provide the data of customer 2, then customer 3, then customer 4, and for each of them we fire the network, and the network that will tell us yes, yes, no, yes. But every time we fire this network, the network is done. Nothing is, so to speak, left inside the network, and it is ready to be used for the next customer, for the next X vector, from which we will derive the next Y vector. We now discuss a different kind of networks that we called RNN, or recurrent neural networks. And the main aspect to notice is that we want to use the networks to operate over sequences of data. So sequences mean, as we said before, that we have several occurrences of a data structure, a data set that we want to be able to operate on. So to operate on a sequence, we must let the network do his job on one occurrence, on one symbol, one element at a time. So we introduce time steps. We introduce the concept of using the network, not just once, not just in a single shot, but in a sequence of steps. So if we look at the picture here on the lower right, we can see that here we have an unrolled view of a neural network. So here the green box is always the same network, which is drawn for 4 time steps. So here we have T1, and then the next step is T2, and then T3, and so on. And for each time step, we provide an input, which will be X1, X2, X3, and so on, and which may optionally expect an output from the network. But of course, for all of these to make sense, since the network is operating on the sequence X1, X2, X3, every time we fire the network, we don't want the network to forget what has been processed before. So when we will provide the X4 input, we want this output to be the result of processing a sequence. So the network must be able to maintain a state. A state, which we can represent with the letter H, is something which is kept in the network, or we can draw it as if it was passed from one activation of the network to the next. Another way to draw it here on the lower extreme right, if we can draw the network just once, and we can show that we apply an input and we obtain an output, and for the next step we feed the input to the network, but also we feed the state that was derived from the previous invocation of the RNN. If we open the little green box and look inside an RNN, what do we find? How does an RNN works? So what we can say is that an RNN is, as we have seen before, is getting 2 inputs. One is the input of the network for the current step, and the other one is the previous state here on the left. And we must provide 2 outputs. One is the output for this particular state, this particular step, and the other output is the new state, which is the state for the step T, that we will provide to the next step. And the way an RNN calculates this output, starting from the inputs, it is quite simple. For the state HT, we have here a simple expression where we see here that we use both our inputs. So we use the previous state and we use the current input xt. And the way we process this input is by using what we know very well and we have seen before very well. We use a matrix of weights. So we have two matrices of weights. Each one is used for one of the inputs. And we must recognize here exactly what we have analyzed before. We have a matrix of weight for a vector. So the result of this will be a new vector, which we can consider as a small next layer. So we have two vectors here, and what happens is similar, as we know, as shown by this picture. So once we have these two vectors, what we simply do is that we do an addition, a sum. We sum the elements of the vectors one by one. So the first element plus the first element, the second element plus the second element. So we obtain a vector which is the sum of these two vectors. And the last thing we do is that we pass each of the elements of this vector through another good acquaintances of us, which is a function that we have talked about, which is Tinyh. So the result here is a vector ht, which each element is the Tinyh of this guy, and this guy is the sum of this and this, and this is just a network layer which is obtained by this layer. One is the previous state and the other one is the input, and you have here two matrices of weights, and so we are getting the new state for the RNN. And the output state is even simpler because we just take the state and we multiply it by a third weight matrix. So how does a recurrent neural network learns? It learns by finding the right values of these weight matrices, and these weight matrices get adjusted during learning, and finding the right values for these matrices helps and allows the RNN to solve the problem which we are training it on. About the training of RNN, what we must always remember is that even if we applied it on several time steps, we are using always the same network. So we have only the same copy of the weights. In our case, we saw that the weights are actually split into three matrices. But what we do when we train the network is that for each time step, the function that the RNN calculates is depending on these matrices of weights, which are always the same. So for each step, when we learn, when we try to adjust the output that we have to the desired output, we go and update always these values, single copy, single occurrences of these values. And the next thing to take into account is that the training is done on several steps at the same time. So for simplicity, we can consider that we let the network digest the input and produce the output over time on several time steps. And when we reach this step, we get this output and we compare it with the desired output, which is the red one, which we had liked more. And from this comparison, we get the error. And from the error, we can go back and we can say this state could have been calculated a little bit better, and we want to improve it. This calculation adjusting the weights. And so we go back, we adjust these weights, and we go back here, we look at the state, and we say, okay, this can be improved adjusting these weights. And we go back and we again adjusting the weights. So two things to notice. The first is when we adjust the weights, we always doing small adjustment to the same sets of weights. The second one is that from this comparison at time step 3, we can go back and update the weights and improve what was the state calculations for time step 2, 1, or 0, and for longer time frames, we can go back in step many times, many steps. So what this kind of training is called, it is used the expression back propagation through time in analogy of what we do with a neural network, where we have many layers, we have some inputs here, and we have the output. And from the error on the output, we update the weights on the last layer, and then we are able to update the weights on the previous layer, on the previous layer, on the previous layer, up to the first layer. And this is called back propagation, because the error is propagated back through the layers and the updates are propagated back in the network. Backprop are propagated back through the network. And for recurrent neural network, we can go back also in the time steps, so we can back propagate through time. We can see now how what we have seen before can be applied to the training of an encoder-decoder model. So what happens in very simple terms is that when we get an output from our encoder-decoder model, we will get it from the decoder side. So what we can do is that we can we compare the output that we get with the expected output, we can calculate the error, and we can update our weights in this decoder RNN, which we know is a single network. So what we can do is that we can start propagate through this network and update the decoder network weights a little bit, and then some more, and then some more. And here we will have these weights are the weights for the decoder network that in this case will get updated 3 times. Then when we get here, what happens is that we can propagate our updates to this intermediate state vector, and we can see how to improve the calculation of this vector, working on the weights of the encoder. So we update the weights of the encoder, and we propagate back, and we propagate back, and we propagate back. So here the weights of the encoder gets updated 4 times, and the weights of the decoder gets updated 3 times. And one thing that we notice of this kind of architecture is that when we use the decoder network, the input we provide is always the correct value that we would have expected from the previous step. So here the network gave us ein, and we would have expected ich, and so to help the network, we say, okay, the expected value here was ich, and we can let the network use ich in the next step. And here we would have expected bin, and so when we activate the network for the next step, since bin was the value that was the correct one, we feed the network with this value, and we ask the network to provide to provide its prediction. Its prediction is there, but we would have expected ein. So when we will trigger the network on the next time step, we will provide ein as an input. And so we are back to our encoder decoder. So now we understand a little bit better our RNN cells that we see here, and we know that we have 2 different networks. So this will be, let's say, RNN1, which is triggered 4 times, and we know that from one step to the next, the state of the RNN is fed to the next state. And we see here that we provide 4 inputs words, and then we produce a state vector, and here we provide the beginning of sentence to RNN2, which is a different network. And after we get the prediction of the first cell, we provide the prediction, the right prediction, even maybe if what we got here is not I, we get a wrong prediction, but we provide the right value to the next cell. We provide I, and we expect a prediction, and hopefully is the right one. Anyway, we provide the right one to the next, and we have here another RNN, and we have the state passed from one cell to another, and we have the output of the RNN, which get used to be decoded as an output word. So we said we provide word as input to the network, and we get words as output from this kind of networks. So the next question will be, how do we provide a word to a numerical network, and how do we get a word from a numerical network. So the question is, how do we encode text, how we transform text in a proper way to be processed by a neural network model. And this is the subject that we are going to tackle next. The widely adopted technique to encode text for neural networks is called embeddings. So let's see what embeddings are.